Thank you for this opportunity to present, to make this presentation on the use of indoor carbon dioxide as a metric of building ventilation and indoor quality. I intend to address whether this is a good idea, bad idea, or perhaps just a complicated idea that might work at times. So the key messages that I want to provide today are to make it clear that despite misconceptions to the contrary, that building ventilation and indoor air quality standards do not contain limits for indoor CO2 concentrations, and definitely not for a concentration of 1,000 parts per million. So I want to explain that yes, CO2 can be used indoors as a tracer gas to assess ventilation, but before that is done, the user needs to understand the theory behind these measurements, the assumptions on which they're based, and to make sure that those assumptions are valid. The third point I want to make is that indoor CO2 concentrations are definitely related to occupant perceptions of human effluence or body odor, but not much to other important indoor contaminants. And the fourth message that I tend to convey is that the indoor CO2 concentrations that we see in non-industrial buildings are very unlikely to result in any adverse health effects. So I'm going to start with a background on the importance of indoor carbon dioxide concentrations, how they've been used in the past, review the uses of indoor carbon dioxide concentrations to help understand building ventilation and indoor air quality, as well as some potential abuses of indoor CO2. And those abuses are listed right here. Uses include compliance with standards, which is really the subject of and then as a surrogate or an indicator of ventilation. The abuses, if I can use that word, is to consider an indoor concentration of 1,000 ppm as a de facto limit or a de facto standard, or a value above which one should achieve building. And potential abuse is using peak indoor CO2 concentrations to estimate outdoor air ventilation rates per person without understanding basis for such estimates and evaluating the validity of the assumptions on which such estimates are based. So go back a long time. Indoor carbon dioxide concentration has been part of ventilation discussion since it was first discovered in the 1700s by Persily, and then some years later, Max von Pettenkofer realized found that CO2 wasn't so much an issue as other emanations for the human occupants. And these discussions have evolved over the centuries, really, to focus on how indoor carbon dioxide impacts building occupants, how it's related to the perception of effluence by the occupants, estimation of ventilation rates, finally demand-controlled ventilation. These are really the applications of indoor CO2 in the air ventilation and indoor air quality, that have been discussed over years, and as time on, we've understood them better. But there are many misconceptions out there, and I'm hoping I can cover some of those a bit today. So first, the first question I might ask, or one might ask, is if you're thinking of indoor carbon dioxide concentrations as a metric, what do the standards say? There's a lot of people who think that 1,000 ppm or 1,800 milligrams per meter cubed in SI units is a standard, is on the books. And in fact, it is not presented in SRA Standard 62.1 or the two SEN standards noted here. Neither of them contain indoor CO2 limits of 1,000 ppm or 1,800 milligrams per meter cubed or anything else. They do have informative discussions, not requirements, but informative discussions of indoor CO2 levels to help users understand their significance. Again, there are no CO2 limits in these standards or any other indoor air quality standards. There are exposure limits in industrial environments, which are much higher, a factor of 10 or more than these commonly misunderstood value of 1,000 parts per million. But these are industrial environments with a different population, typically healthier people, from what you see in non-industrial buildings, where you will see children, the people with pre-existing health conditions. And obviously, it's important to maintain, to meet these limits in industrial environments, but it's a different application. And just for example, the U.S. Green Building Council LEED program does require CO2 monitoring in naturally ventilated spaces, and that gives points for such monitoring in densely occupied spaces, but LEED is not a standard. It's a rating system. And while it requires such monitoring or gives credit for CO2 monitoring, it doesn't have any concentration limits. It just says, measure it. Not sure exactly what you do with it, but there's no concentration limit in there. So, to kind of summarize, there are no indoor CO2 limits for non-industrial spaces, and for good reason. This issue of 1,000 ppm or 1,800 milligrams per meter cubed is really related to perception of body odor. Starting in the 1930s, there were a number of studies conducted in environmental chambers, which were repeated in buildings, in which people were housed in these chambers, and other individuals came in and basically rated the air, perception of the air with respect to bioeffluents. These studies found that 79 liters per second per person of inhalation air led to acceptable levels of body odor perception for most individuals entering with fresh hoses from clean air, and about 80% acceptability. And it's really the basis for a lot of ventilation requirements that we use in standards and building regulations around the world, specifically acceptable levels of body odor perception. In some of those studies, they also measured carbon dioxide. At the same time, they measured ventilation rate, and they found that that the level of acceptability of body odor perception occurred when the CO2 concentration in that chamber was about 1,250 milligrams per meter cubed, greater than outdoors, which is about 700 ppm. And if you add a typical CO2 concentration up with the 100 milligrams per meter cubed or 1,000 ppm number. So basically, this 1,800 milligram per meter cubed or 1,000 ppm CO2 number is on its consistency with ventilation for achieving acceptable levels of body odor for with freshes. That's really what it's about, and it's valuable in that respect, but it's limited. There are a lot of other important pollutants, as noted in the last line of the slide, many other important indoor pollutants that are not associated with the number of occupants. These are pollutants come from outside. These are pollutants associated with emissions from building materials and furnishings and others. So this, the E2 is useful for capturing measuring the acceptability with respect to body odor, but it's not a very good metric for the many other important pollutants that don't relate to the number of occupants in a space. Another important thing to think about, and of great interest recently, is what does CO2 do to occupants? I measure the industrial limits of as high as 20 to 50,000 milligrams per meter cubed. In buildings, measures are rarely that high. And as I mentioned earlier, those industrial limits are not applicable to the occupants of non-industrial buildings. That's children, the elderly, people with existing health conditions. And I've already mentioned that the 1,000 ppm or 1,800 milligrams per meter cubed value, while some view it as a de facto standard, it's not based on any health impacts of CO2. It's linked to outdoor air rates of nominally 7 liters per second or 15 cm per person, and the rates on the level of ventilation rates of that level do a good job controlling or for acceptable levels of body odor perception. As ventilation rates go down, CO2 concentrations increase, and the concentrations of other pollutants that are generated indoors also go up. So there have been studies, as noted in the third bullet, there have been studies where CO2 levels are correlated with increased symptoms on the part of the occupants. But it's very likely that those symptoms are associated with other contaminants that are also increasing with lower ventilation rates. So the ventilation rate goes down, and all the internally generated contaminants concentrate go up, and those are probably causing the increased symptoms, not the CO2. There have been some recent studies showing that there are some increased performance in terms of decision making for concentrations as low as 1,800 milligrams per meter cubed, but there are recent studies that haven't shown this effect. So it's unclear whether that those concentrations really impact performance. I think we're learning more. It's not time to rewrite all the standards based on this, and probably not time to work out concentrations of this magnitude and to start the way we ventilate buildings as a result. So let's additional research finds, but there is disagreement on this issue. So this slide just kind of summarizes some measurements of indoor CO2 concentrations from the literature, and it's broken by office buildings, residences, and schools. I won't go through this in detail, but I will note that most measurements of indoor CO2 concentrations are less than 2,000 milligrams per meter cubed, or somewhat higher than 1,000 ppm. Most measured values are below that. A small fraction are above 5,000, but none industrial limits. So in CO2 concentrations are low, and they're low relative to the industrial limits, and even low relative to this matter of 1,800 milligrams per meter cubed. I intend to do some additional work to gather other summaries of measured indoor CO2 concentrations, but I think it's important to take a look at what people are actually measuring, and most measurements are low relative to 1,800 milligrams per meter cubed. A place that we often see people using indoor CO2 as a metric is to use it to estimate outdoor air ventilation rates per person using this steady state mass balance equation shown in the box. And this is a basic case. You're using carbon dioxide as a tracer gas, and we've been using various tracer gas techniques for almost 100 years, and there are well-established standards for doing so. And in this, whether people realize it or not, they're doing a single-zone, constant injection tracer gas technique. However, to use this technique reliably, there are many assumptions implied that not all users understand or attempt to validate. And these assumptions include that the exchange rate is constant, that the CO2 generation rate is constant and known, that the space being studied can be characterized as a single zone. If these assumptions are not valid, the estimation will not necessarily be valid either. And in particular, the assumption that the CO2 concentration has achieved steady state in the space, if that's not valid and you equation before it happens, you will tend to overestimate the air change rate. I used earlier some of the potential abuses and uses of CO2, and the abuse category, I included 1,800 milligrams per meter cubed or 1,000 ppm as a definitive IAQ metric. Another would be thinking about the health impacts. At levels, there is not strong evidence that there is any health impact. And at the level of interest in industrial environments, we just don't see those in non-industrial buildings. And another potential and common abuse is using peak CO2 concentrations to estimate outdoor air ventilation rates per person without evaluating the validity of the assumptions. Use CO2 as a convenient tracer gas. You've got a built-in injection mechanism in all occupant buildings. It's a potentially useful indicator of ventilation per person if properly. And then finally, I mentioned this earlier, and I'll mention it again, demand control ventilation, using CO2 to estimate or to control outdoor air ventilation rates so you provide enough ventilation for the occupants in space and don't overventilate and consume area amounts of energy. So conclusions, there's still, after all years and all this writing and all this talking, there's still confusion about what indoor CO2 concentrations relate to ventilation and indoor air quality. The so-called limits and standards are either a steady-state value linked to ventilation or a health-based industrial value. There are limits down to health effects of CO2 in industrial air quality standards. Most measurements are below the number of 1,800 milligrams per meter cubed, and I haven't seen any that are in the range of the industrial limits when in non-industrial buildings. Carbon is a great tracer gas, but you still have to do the math. You still have to do the mass balance analysis on which tracer gas techniques are based. And then finally, how do we address this confusion? Well, we can write reports and papers, and that's good if people read them. Training can be useful. Webinars like today, if viewed and thoughtfully, that's great. When people review journal papers, they should, where CO2 is used as a metric or as a tracer gas, it's incumbent on them to take a really careful look on the science behind that. So I believe that we can put this confusion through, more awareness, more events like this, and I'll do all I can to support those efforts. So thank you very much.